we have this concept of rockets, okay? How do rockets work? Okay, I'm not going to talk about how magnets work, but rockets, this is the idea. Here you are in outer space. There is nothing around you. I don't have air. I cannot take the air and push it that way or swim through the air like an airplane does, basically with a propeller, correct? Okay, yet I can generate thrust. I can generate a force this way, and I do it by taking molecules. Okay, in the case of NASA rocket, Saturn V rocket, this is water. We're combining hydrogen and oxygen, I believe, is what they did. Okay, or maybe it was kerosene. Okay, but anyway, there's some molecule. I'm taking water molecules and I'm flinging them this way really fast, like 2,000 meters per second, and there they go, right? Okay, and every time I throw one of those, right? Whoa! Okay, every time I whoa! There we go. Every time I throw one of them that way, I exert a force on the molecule that way, but the molecule exerts a force on me this way, correct? Okay, now, does it matter what happens to those molecules after they leave my hand? Does that affect the force on me at all? No, I could be throwing them off a cliff into the Great Rift Valley, and I would get the same force off of them that I would if I was hitting a wall there. The only exception would be, I don't know if you noticed, but like one of those handballs or racquetballs almost hit me, yes? Then I would get more force if it like bounced off of something and hit me. But most often when we have a rocket, we don't want the white hot fiery gases to then strike the rocket again. Okay? So anyway, that's the notion, is that rockets are not pressing off of the ground. They're pressing that they fire behind them. Okay? And I think I have a video for you guys, so let's look at the video. And where is it? It is here. It's probably on YouTube, but I'm just going to go and find my copy of it.
PF6s that weighs 623 feet long and mechanisms.
Here we go.
One engine produces 50.
That's quite an accent. Now the
This has got 4 of them. But 58,000 pounds of thrust, that's kind of meaningless. How do you get your head round that sort of power? Our plan is to drive a car behind the 747 when the engines are at full power. The question is, how far can the engines blow the car off course?
It's not as easy as you might think. It's too dangerous to drive them under here, behind the engines. They have to be well clear. In fact, they have to be way back here, past the tail, and then a bit more. That's a good 50 yards behind the engines.
Remember,
The car will be subjecting to a good stiff breeze is this Ford Mondeo. Modern, aerodynamic, good at coping with motorway crosswinds.
motorway crosswinds.
Right, here we go. The pilot is easing up the throttle, building up the power.
Notice he's only pushing 2 of the engines forward. There are
Now it's
4 levers,
we
correct?
release the car at exactly the right time. Because if these engines run at full thrust for more than 20 seconds, they'll start to rip up the runway.
They'll rip the runway up. They'll melt the runway.
Okay, the engines are at full power, and here comes the Mondeo. Now, can they blow this 1.5 ton car off course from 50 yards away? 3, 2, 1, blimey, there it goes!
I like the Lord of the Rings soundtrack.
The Mondeo must have been blasted a good 50 feet, but we haven't finished yet.
Well, that was a modern, streamlined aerodynamic car. So let's have another go now and see what happens when we let loose the top gear crosswind on something a little more, well, slab-sided. A Citroen 2CV.
Big engine, lightweight hippie car. Okay, here we go again. The engines are up to 58,000 pounds of thrust. The car is released. And 3, 2, whoa, crikey! Yes, the 2CV really doesn't like crosswinds.
I like that car.
Well, there you go, you see. Next time you're out, you think you might encounter crosswinds or have to drive behind the 747 at takeoff thrust, you're better off with a Mondeo than a 2CV. It's a service we provide this stuff, you know.
I like the French. Okay, here, let's go. So that's kind of cool. I think the most impressive thing is that if they run it for longer than a certain period of time, it tears up the runway. That's kind of amazing, yeah. I don't know. What is that from? I don't even know. Did it say Top Gear? Yeah, Keenan watches Top Gear. Oh, you've got all that. Okay, I'll log you on here in a sec if you want to type those in. So let's go back. Let's go back to here. Okay. So this is the simplest kind of rocket. This is a solid fuel rocket, and I think I've got some of these guys sitting around. I had one on my counter. Solid fuel rocket. But anyway, the notion here is that it's full of something like gunpowder. Okay, only it doesn't go boom. When you light it, it goes shh, right? That's the fuel, and then okay, this is sad. Do I want to pass around a perfectly good one? Maybe I do. I don't know. I think I've got a regular old. Here we go. All right. I don't know what happened to my used one, but here's an unused one. Just don't light a match to it, you know. There we go. It's got the fuel is in there. This is the nozzle. It's actually made of clay. It looks like the same stuff here as here, but it's not. Okay. This nozzle here is made of clay. The body is made of just like a really, really hard paper. Okay. And this thing, the nice thing about a solid fuel rocket is that they're very uncomplicated. These have been around for hundreds of years. This is the original thing that the Chinese developed. And there's a fine line between a solid fuel rocket and a firework, yes? In fact, when I was teaching at the Indian School, we would take these rocket bodies and recover them and then just fill them with like gunpowder. Is this on YouTube? Anyway, and we would put them as a final stage, and it would just go kaboom. We could make our own little like skyrockets, and they would sound like M80s. So if this fuel burns too fast, of course, it's going to burst the container, and that's always the danger with a rocket, is that the pressure you build up inside to get a really strong exhaust gas velocity is going to burst the sides of the rocket. And a good rocket is engineered so that it's close to that, right? Because remember that the thrust you get from a rocket is really the mass burn rate, right, times the exhaust gas velocity. Well, you want this to be as small as possible so your fuel lasts as long as it can. Therefore, you want this to be as big as you can, right? Well, to make a big exhaust gas velocity, you have to have a tremendous pressure inside your inside the engine itself. The nice thing about a solid fuel engine is that it can sit around in your backpack, and you can walk around in the desert, and if you ever need to kill a Soviet helicopter, you can just pull that thing out and go boom, and it just launches, right? So solid fuel rockets are highly portable. They're very low maintenance. It would be somewhat more detailed if you had to put like liquid oxygen and liquid hydrogen into the rocket. The helicopter's going to be gone by then, right? So there we have it, right? These are the largest solid fuel rockets ever built, I believe. Okay, but they use them for like jet assist takeoff to help airplanes on short runways for takeoff, right, in a military situation. But these things here are solid fuel boosters, right? And the Challenger failure in the 80s was when one of these things are joined in segments there. When one of those segments leaked white hot gases, and then what you can't see very well back there,